Hello and welcome to another episode of the Clojure Pills screencast. This is episode number 10. The function we are going to discuss is into. Before we start, a quick mention of the book I'm writing for Manning, the Clojure Standard Library, an annotated guide. The content of the screencast and the other screencasts in the Clojure Pills series is based on the book. So if you enjoyed the screencast, you might very well enjoy the content of the book. I have a 42% discount code displayed on the screen, SSBorgatti if you use it at checkout, and the link to the webpage of the book is displayed below, and the next one is my Twitter handle at reborg if you have any question. So into is a quite simple function, and it's got two main arities. One was recently extended to allow for the use of transducers. And it's basically returning a new collection. And this new collection consists of the content of another collection that is passed in as input. Let's see what we can do and what our interesting thing about into. So I have some basic example. So you can change the type, so to speak. So it's quoted because we are not changing the type of an existing collection. We are always creating a new collection. Everything is immutable in this case. So in this case, for example, we want to change the type of a collection, which is a lazy sequence range 10, into a set. And what into is doing is taking the content of the from collection and putting the content into the to collection, in this case of type set. We can clearly do the same with vectors and we obtain similar results. We can also use other collection types, for example sorted set, to make sure that even if we are using a set, we are still putting elements, items in order inside the set instead of being unordered as it is usually the case. And finally, if you give a specific format for hash maps, which is a list of pairs, then you can also copy or change the content of the collection of a vector, in this case, into a hash map. What is enabling this is basically the conj semantic, meaning that the way in which into will move the content from one collection to another is based on the semantic of conj. And conj, by the way, is what the implementation of into is based on. So that means that if you move elements from a vector into a list, then the semantic of conj for list will append the elements at the beginning of the list instead of the end. So one will be the last. And as you can see, the output collection from into is apparently reversed, is in reverse order. We can use also other data types, and one data type that is commonly used with into is the persistent queue, which doesn't have a constructor, a function, a reader literal like many others of the collection. It doesn't even have a constructor in Clojure code, so the only way to use it is to import the persistent queue like this with import, and then into is able to push elements into the queue, and you can then use the result, like the queue that I called with a single letter Q, to inspect the content of the queue and so on and so forth. This was just an example, not to show the conj semantic, but to show that you can also push elements into other kind of collections. There are a few corner cases that we can have a look at. So an interesting one is the case. So this is not really an edge case, but is considering the fact that the output collection is not necessarily, doesn't need to be necessarily an empty collection. So in this case we have as the target collection a range, and we are asking into to put another range into the first range. And as you can see, the result is similar to a merge operation of the two lists in this case, that they are merged together. And as you can see, the conjugate semantic is reversing one of the two lists, the target list, sorry, the input list into the target list. Instead, talking about corner cases instead is the fact that you can into a nil. In this case, this is converted into a default empty list, and so as you can see, we are doing the equivalent of into empty list of a set 1, 2, 3, and that will obtain the same result. So nil is a default for empty list. And you have this strange syntax here that you can into a nil into nil, and that will return a nil. So you are free to use as many nil as you want. You won't throw exception, but you're probably definitely not going to use this explicitly for any practical use. We briefly said at the beginning that into has an additional RET that understands transducers, so you can use it simply by invoking into with a third argument, and this is placed in the middle. So into the first argument is the target collection. So in this case I'm using another type of collection, so we can see another use of into for another type, in this case a vector of primitive integers, and we are passing a transducer. So the transducer is basically transformation that we are asking into to execute against the input collection. In this case the input collection is a range, so we're asking into basically to take the content of range, process it through these transducers, which is the composition of an increment and a filter, and to put the result into a vector of primitives. And this all work nicely and as expected. Another aspect that might be interesting or might be useful is to see what happens with the metadata if you happen to use them. So metadata are not possibly one of the most used features in Clojure, at least from a perspective of the final users of Clojure libraries or Clojure code or applications. But library implementers or sometimes also application implementers are using metadata to decorate internal data with additional data, which is exactly the definition of what metadata is. So they can be used to mark as a marker for specific data in order to avoid to inject some specific signal that will go inside the content of some collection, and then you'll have to remember to remove it. Is at the end, is at the beginning, so you need to do all this logic. And if you use metadata instead, that additional content and decoration is just staying outside. And you also got this with meta and meta functions from the standard library to deal with metadata, which are nice. So I prepared an example to show how into handles metadata. I have a function called sign. This function sign is taking a collection and is adding replacing the metadata of this collection with a map that contains a key signature and like the string concatenation of the elements inside the collection. And this is just to show that if we use into and we sign the target collection, which is a vector in this case, and we assign the input collection, which is a range of 10 in this case, we should be able to verify if the metadata of the output from into are taking the metadata of the target collection or the input collection. And as you can see below, they are taking signature 1, 2, 3, which means that into is propagating the metadata of the target collection and not the metadata of the input collection. That may be what you expect or maybe not, but something to consider. Something that into is not enabled for are basically all the mutables collections, and the reason is that is part of the implicit contract of into to return something that is immutable. And by the way, for some of these mutable collections there are specific functions that you can use instead of trying to use into. So if you try any of these, like into a transient or into an array or into like a Java collection, it will fail, and reason is it will try to cast, or it will verify that the input collection is that the target collection is I persistent collection, and if it's not, is throwing an exception. So you don't want to use into for these cases, but there are, for example, for arrays, there is into array, a function in the standard library that you can use in a very similar way with an implicit target, which is an array. So into array, I think you specify the type like this, and then you pass the argument as a collection. Anyway, this is dedicated to into, so we're not going into the details of into array in this case, but there is a function for that. A little bit more involved example I want to show you in this episode is a way to maintain the original type. So what I mean by that is into is basically designed for you to be able to change types or to create new collections, which are usually of a different type of a target of an input collection. So the reason you do this, why you have into, is because in some part of the application you need to take advantage of the features of another kind of collection that you don't have as input, and maybe later on you need to return or to transform it back again to the original collection. One example for that would be to into a vector into a set to remove all duplicates. That would be taking advantage of the collection type set to remove duplicates from a vector, and you could use into to do this. But what I'm proposing here is like a less surprising into that is maintaining or trying to maintain the type of the input collection. It's doing this for simple collections, it's not doing this for everything, but is fair enough for what I want to show you. So this function maintain is taking a processing function fx and a mapping or a filtering function, or like another function f, and a collection which is the input collection. You see that with these two functions what is happening is it's applying the first function using the second function as a higher order function as the processing rules for the input collection, and then is use empty, which is the key for this to work, to into the content of the input collection into the target collection. Empty is the key because empty is creating a collection of the same type of the collection you're passing as input. So what happens if I do this? If I, for example, pass a set as an input collection to maintain, and I want to do a map increment to this set, if you don't use maintain, the map increment will transform the set into a sequence, and then you have to deal with the fact that you have a sequence instead of a set. I'm also applying a filtering, which is giving the same result, so sequence in, sequence out. But using maintain, I'm forcing at the end of the computation the target collection to become the same type of an input collection. So we've got like a map and a filter transforming the set into a sequence as an intermediate result, and then going back into a set again, because I'm using into and I'm using empty to do that. Another example here is just a different target type. So I have a hash map as input, and I'm expecting a hash map as output, and I'm expecting this processing to happen in between. So not sure if this will be ever useful to you or in one of your applications. I think it's more an illustration of the use of into and empty to transform collections from one type to another. Finally, I'd like to talk about implementation details and performance. So the implementation is quite simple. Let me make this bigger. But essentially, into is based on reduce and conj. Those are the two main operations that needs to happen in order for into to work. One interesting thing that we are going to verify now in terms of performances is that if the target collection, so to collection, is editable, and that means can be transformed into a transient, then into is taking advantage of that, or basically reduce is taking advantage of that. So the target collection is transformed into transient before, and it is made persistent right before coming back. That speeds up things, and we'll see in a second in which way or how much is going to speed up things. And if it's not editable, is a normal reduce with conj. So you could basically replace into with reduce conj to from, and it will work the same way. But into, apart from taking care of a possible transducer in the second RET is also taking care of, can I make this a transient, so you don't need to think about it, which is handy. So let's go back. I prepared a little benchmark using Criterion. I have this macro that is extracting just the mean execution time for the map that Criterion is returning, which contains many more interesting data, but at the moment I'm only going to show you the interesting bits. And I started the execution of the benchmark, so I'm calling the macro B into like over this form that contains into a list of a big range of numbers, and we are going to test right after that the same operation where the target collection is a vector instead. So the difference between the two is one is editable, the other is not editable. The first one is the persistent list does not support transients, so it's going to follow the normal path of reduce with conj. Instead, vectors supports transients, so is using transient and then persistent pattern to create the target collection in a mutable context and then go back to an immutable context that you don't see if you're just a client of the function. So the first result came back, and the second came also back, and we can see roughly like, what is it? It's probably 6-7 times faster. We are going from 0.13 seconds to 0.027 seconds. So it's definitely much faster when transits are supported. So keep that in mind when you use into. If you are doing an into of larger collection and to a persistent list for any reason, be aware of the fact that it might be a slow operation depending on your requirements. So I think that was all I wanted to show. Well, not exactly. I forgot about this last bit. I just put the same benchmark into a chart with list and vectors. The chart is showing like 10 samples of the same benchmark running on an increasingly bigger collection for both into a list and into a vector. Is not perfectly straight line, but this is because I'm using quick benchmark and the fact that I have only 10 samples. By making this larger, the two lines should be roughly straight lines, and this to demonstrate that the behavior of into is roughly linear. So it is linear in number of steps based on the based on the number of items in the input collection, with the difference that with increasingly larger collections, the being able to transform the target collection into a transient is making things faster. So you can see the yellow line is diverging and is staying with smaller numbers compared to the blue line that instead is going more to the right with increasingly higher times. So now I think that was all for this episode of the Clojure Pills. As usual, the show notes will be up, and I'm going to edit this as we speak with the right name into. And I hope you enjoyed the screencast, and this is all, and I'm almost done with my online change. So thank you for listening, and until the next episode, goodbye.